And here we go.
There you go. 50 plus.
50 plus, we'll get going then. Good evening. As you can see, I'm Andy Snell and this is my hair that still needs a cut. Massively so. Yeah, but I refuse to have it shaved, so it's not happening. So it will just get longer and longer then. Tonight we're doing stability and control. I'd like to thank the people who allow us to post onto their Facebook pages to push and promote what we're doing. That's really good. What names are we? We've got Woody.
We've got Woody, Peter.
Oh Christ.
Right.
I speak to all of them.
All of them, yeah.
And many more.
Many more. All you guys that let us post on your Facebook pages, absolutely fantastic. We're getting a great response. I'd like to thank Will for Sunday night. His daughter had been ill the last few days, but she seems to be doing a lot better. So happy about that. But if he looked a bit tired, that is why. He'd been up with her for 2 nights. And thank you for coming on and doing some RT stuff, an introduction into why we should perhaps look at getting our RT licenses and the safety aspects and all the good reasons that we should actually do that, including myself. We also had somebody who said, can we look at synoptic charts and give a quick forecast for the day? Yeah, we can. We can't do it every day. We are busy. I've been out building all day. So we are busy around here doing stuff, getting stuff ready for when we reopen. Stuff we always wanted to do but never had time to do. So that's really great stuff we're doing, but which doesn't give us time. But we will look now at a synoptics chart for tomorrow. And this is from, let's be sure, this is valid 0, this is midnight. Okay, let's just look at one tomorrow. So let's look at 12 o'clock tomorrow. Okay, I'm going to show you, I haven't printed it out. So just tell me when that is in focus there. About there. Okay, so we've got this high pressure region, yeah, which is going to give a pretty easy forecast for us. I would predict tomorrow in the Midlands, in the centre here, yeah, the centre, this high pressure is just gradually pushing across and dropping. It's dropping by 2 millibars in pressure overnight. At the minute it's 1027 and dropping. I predict a light southwesterly and clear skies. It won't be cloudy, and the reason for that is, if I go to a 214 and show you a current 214 on the Met Office, if it allows me to, low level, so I'll click on low level. I'm going to click on the 214 on the Met Office here, so I'm going to click on the 214 and I'm going to zoom in to the box in the centre, which is about where we are, and there it is there. Okay, now I've put that on the board. And we've got, this is today between 1500 and 2100 hours, and later on 21 to 0300 hours. Okay, and what you will notice here, 1,000 feet, wind direction 170 at 5 knots, temperature +6. 2,000 feet, sorry, it's 170 degrees, 5 knots, +3. So which means between here and here, this 1,000 foot gap, it drops 3 degrees, which is a lot. That's quite a high lapse rate. That would say to me instability. Boom, things will take off. Things will go a bit mental. All right? But the interesting thing is, if we look at 5,000 feet, yeah, look at the wind change, yeah, 030, still 5 knots, but look at the temperature. The temperature is 5 degrees. It's 2 degrees warmer than at 2,000 feet. So in 3,000 feet, the temperature actually goes up. Also, later on, slightly different and different there, yeah, a bit different in wind speed, but also it goes from +7 to +5, only 2 degrees drop over 1,000 feet, we've got a lapse rate of 2 degrees per 1,000 feet at low level, but at 5,000 feet, plus 6. So if any of you were watching the lecture on MET the other night, what does that tell you? It tells you that ground, we've got high pressure pushing the air down. Overnight we have a layer of cold air. The air on top is compressed and creates an inversion. So we've got an inversion over the top of us. So this 3 degrees lapse rate here, now if this was only 1 degrees, yeah, this whole forecast would be totally different. It would absolutely go ballistic. 3 degrees lapse rate at low level, 1,000 feet, this time of year, things are going to be going up like rockets. Because of the inversion, tomorrow it's going to be a blue day. Beautiful blue day. Ideal day for growing tomatoes or laying bricks. Beautiful. All you guys that are into your XC, yeah, it's crap. You're not missing anything, so don't worry about it. Yeah. All you guys who want to fly across country, it'll be a bit murky anyway, so don't worry about it. Yeah. Don't worry about it too much. It's not all great. It's just going to be a beautiful blue day. So get out in your garden and enjoy your garden. Yeah. As Alan Titchmarsh says, no matter what the weather, enjoy your garden. Okay, and that's the forecast basically that will go into tomorrow. If you look at 214s tomorrow, they might differ a bit, but I don't think the inversion is going to break down until the pressure pushes away even more. And when it does break down, it might go a bit ballistic. We might have rain later in the week as this big high pressure pushes away. Okay, I'm just like a weather girl on TV. As this high pressure pushes away. Yeah. So yeah, forecast tomorrow, blue skies. Yeah, sunny. Go and grow tomatoes. That's what I'm doing. Lay bricks. You all got that? Happy days. Right. Stability and control. I don't know anything about that. I'll just point things where I want to go. So stability and control. Mark's going to come on. He's going to do some a lecture on stability and control, or lack of at times, and what that's all about. I'll see you guys later. Thank you very much.
Hi guys, welcome back to Airways Airsports, and thank you to Andy, if anyone can understand the weather quite as well he does. I'll eat my hat. Very good at forecasting. We will do some more on MET. We're going to do some more on all of the topics. But the last lecture that we gave here was to do with the principles of flight. So it kind of made sense really to follow on from that and go into stability and control. Why stability versus control is probably the better way of putting it. So stability versus control. And it's the versus bit that's the bit to remember, because you can't have both. Inherently they combat each other, because something that's stable is going to be a lot harder to move around, and something that moves around very, very easily is going to be very hard to maintain stable. And this is purely now down to the kind of aircraft or flying machine that you fly, because the aircraft or wing designer will design a wing to either give you stability or control. And it puts us on pretty much a sliding scale. Stability be down this end, all the way up to control, which is on this side. And what I want you to imagine is, again, we've probably used this analogy before, but all the way down here we have an airliner that's going to take you on your holidays. No one wants to be bounced around in an airliner. You want to sit down, drink your drinks and have a comfy flight. Whereas all the way over to the other side we have control. So these are your fast jets that want to be able to outmaneuver the opposition, or to be able to put themselves in a position as quickly as possible. those pilots aren't looking for a stable flight. They want to be able to do their job. And so an aircraft or wing designer will design either an aircraft to be stable or controllable. Now for us, for the type of aircraft that we fly, particularly as instructors, our aircraft tend to sit somewhere in the middle, where it's a nice balance of stability and control. And this is why we say versus. Particularly when we're talking about paragliders, and I've been discussing this with Barry in somewhat, you have different grades of wings. So you have A all the way through to D. There's the one, all the way through to D. And I first was saying, oh yeah, it's a beginner wing or a first wing, and Barry's like, no, it's your first wing. It might also be your last wing. And so, same on the A, B, C and D's, you will see that they will sit there depending on what type of wing you're flying in order to achieve whatever it is that you're trying to achieve. And the same if you were to break down and look at this particular section in more detail, you might find something like a GT 450 might sit more on the stable side, and something like a Quick or possibly a Quick will be more on the controllable side. And so even within this little bubble, we'll find our aircraft will be one side or the other. Now this brings us in really to look at that stability versus control, because any aircraft has 3 axes of movement. And it's the aircraft designer's aim in order to make those axes either more controllable or more stable. So let's have a look at these axes. So apologies for my terrible plane, so here we go. Not going to win any awards on that. So first of all, we have the lateral axis. The lateral axis runs pretty much straight through the wings, and this is our lateral axis. We also have our longitudinal axis, and this runs through the keel of the aircraft. So long, easiest way to remember it, the long is the long portion of the plane. And we also have, I'm not going to fall out these pens tonight, a vertical axis. Now, flex wing pilots, you do have a vertical axis, we just don't have control of it per se, but we do still have a vertical axis. So here we have our longitudinal, lateral and vertical axes. The point in where all of these 3 meet tends to be the centre of gravity. The aircraft designer has designed the aircraft to move around this adjoining point. And so, just to bring some labels on this, when we're talking about control, we're talking about the movement of these axes. So longitudinal would be pitch up, pitch down. Lateral would be rolling left and rolling right. And vertical would be yawing left and yawing right. Obviously, we pitch on the lateral axis, we roll on the longitudinal axis, and we yaw on the vertical axis. And same with the flex wing. If I have a model, for the flex wing model, exactly the same. We have pitch, we have roll, and we do have yaw. The aircraft does move in this direction. Now, an aircraft can be moved around these 3 axes in varying different ways. The aircraft can be disturbed. It can be bubbled by some turbulence or maybe some gusts, or we can choose to control the aircraft. So there are two ways that the aircraft can move around these axes. And knowing on how this aircraft will react, or your aircraft will react as it's disturbed from these axes, is something very useful to know. How quickly will that nose come back up? If I carry on with the roll, what would be the further effects? And this is why stability and control, or understanding the stability and control of your machine, is very, very important. I keep coming back to this. Aircraft general, or understanding principles of flight, really will aid you in your flying ability, certainly in your decision-making process. Knowing that the aircraft's nose will do this, knowing that it will stall at when and how it stalls, etc., etc. It really will build you with confidence. And I appreciate that if you're a student looking at this and going, well, I've only done 4 hours, it comes with time. This is the experience side of things. The reason why your instructor is sitting there all laid back, holding the stick or bar with 2 fingers, and your white knuckles gripping onto it like it's a fairground ride. He's got more experience in that aircraft. He knows it's not going to drop out to the sky. And reassuringly, in no time at all, so will you. Okay. So, there are 3 types of stability that we need to be aware of. And again, an aircraft designer will use these 3 types in varying things. So we first of all have positive stability. Now, positive stability, if we imagine that this is a neutral plane, positive stability shows that once one of these axes has been moved, is how quickly it will return back to its original form. So with a positive stability, you will get the deflection or disturbance, and eventually it will return back to its original flight plan or its original state. An easier way of imagining this is a U. So there's the ball, we push it down the slope, it's going to roll up and then it's going to roll back. It won't go as far and it won't go as far again, and eventually it will settle at the bottom. Now the other side that we have is what's called neutral stability. And again, if we have a level plane, neutral stability is where once the deflection or the input has been put in, it will remain at that state. It won't get worse, it won't get better, it will remain exactly the same. So if we're looking again at this frequency, it will be exactly the same all the way along. An easy way to remember this is that same ball with the input. It will continue to roll at the same speed and not get any worse, slow down. It won't increase in speed, it will stay the same. And the other side that we have, the final one, is negative stability.
We've had that.
That's neutral. Neutral stability.
It just looks like negative.
Maybe, yeah, NEU, sorry. NEG. Negative stability, obviously, unlike these two, will get progressively worse. So once the input is put in, it will increase and get worse. So again, an easy analogy is a ball on top of a hill. We push the ball and it will accelerate as it rolls down the hill. So where can we see these in practice? And this is something when we do get airborne or you're next in an aircraft that you can practice, because you don't want to be recovering the aircraft in a way that the aircraft, you're now going to be fighting it. All aircraft are positively stable in pitch. So as an example, if I was to pull back on the stick and then let go, the stick, it would return back to neutral. The aircraft would initially climb and then it would descend and eventually it would return back to its original state. The reason being, we pull back on the stick, we select a nose up attitude. As the aircraft starts to climb, it's generating more lift, therefore it's generating more drag. The drag slows the plane down, reducing the airflow over the wings, and therefore the lift is reduced. As that lift is reduced, the nose comes down. As it starts to accelerate, this time the airflow over the wing increases, generating more lift. And so therefore the nose comes up. We're now generating more lift, and so on and so forth. So it's all to do with the airflow travelling over the wings. And also to do with where the manufacturer has positioned the weight. We'll come on to this in a moment. In that the weight will be pulling the nose down. But most aircraft, all aircraft, should be positive stability in pitch. When we're looking at neutral stability, this tends to be, in most machines, in roll. And what happens is, if I select a bank angle and return the stick back to neutral, the aircraft will maintain that bank angle. There are other things that may come along, but ultimately this aircraft won't be looking to return back to its level plane. It also won't be looking to increase its bank angle. We'll say we won't go past 30 degrees, for those of you who know a little bit more. And so it will stay there, and that's great should you want to be taking a picture. We'll be that side, won't we? Taking a picture or having a look at something on the ground, or flying over someone's house so that they can have a look. You can set a up to 30-degree bank angle and the aircraft will remain in that state. When we're talking about negative stability, this probably is more to do with the vertical axis. And again, more to do with the aircraft design, because once we put the input in, the aircraft yaws, but then what happens is this wing going faster. I'll do it this way, so we yaw. This wing is now going faster, generates more lift. This wing going slower generates less lift. So as we yaw, the aircraft will start to roll. And so, if we were to put any description in, negative stability will be probably more to do with the vertical axis. But it really does depend on the type of aircraft that you fly. And so there we have it. We have our axis and the control about those axes, and the three types of stability that are within your aircraft. Right, any questions so far? No. Have we lost about 50% of the viewers?
Let's say hello to the people from Spain.
Hello to Spain. And it was on the other, Puerto Rico. They seem to be back with us quite a lot.
And Liverpool.
And Liverpool, yes.
Steve Buckley.
Hey, Johnston.
Okay. So the question is stability a good thing? Well, yes and no, because you don't want to be in an aircraft that is so stable it's near on impossible to move. You want to add an element of control in it, or instability, less stable, so that the aircraft can be moved. And again, depending on the type of aircraft, I have a few examples for you. But here are some examples that we have here. So we have a Cessna 152. It's a high wing aircraft. It's a trainer. It's a trainer or a tourer. We want the aircraft to be very, very stable, and therefore it's harder to control. As opposed to the Spitfire, which we don't want to be stable at all. It's a low wing aircraft, but therefore it's got lots of control. So yes, is stability a good thing? The one thing that they do all have though is that positive stability in pitch. The Cessna will return back to its original state sooner, but both aircraft have positive stability in pitch. And so why is that? It's a good question. And one, certainly as students, you might sit there going, well, because my instructors told me so. Yeah, very good, but never just take because somebody has told me so. Understand your aircraft, understand your flying machine and why it happens. And what I want to go into now, and this is where a lot of flex wings pilots are going to switch off and just listen to it. Don't. It's the same to you. What we are aware of, or what's drummed into us, is here's an aerofoil. acting up, we have lift, and acting down, we have weight. The two forces are opposing each other. That's what we're told. Lift opposes weight. Now I do need to make a correction. I was talking mass a lot on the last one. Obviously the force acting down is weight, the mass is the weight of the aircraft. But an aircraft designer will position that mass in order to influence the weight force. And in order to create positive stability, they need to move the weight or the mass forward of the centre of pressure. And so if we're looking at an, can we see this okay? A manufacturer will position the weight further forward. So the weight is acting down. But he will position the lift or centre of pressure there. This sets up what's called a couple. And so now where you have lift acting up and weight acting down opposing each other, you now have the weights further forward. So the weight will pull the nose down. Yes? And it's setting up a couple just like this. So the weight will pull the nose down, the lift will pull the nose back up. Yes? It's working this way. Now the argument there, or seeing now the theory and the actual position is, if that's the case, you see I've marked this up, you see the centre, I've got these wrong, there's the weight, centre of gravity, and there's the centre of pressure. Why then, based on the actual scenario, doesn't the wing do that? Because the weight will be pulling down. The lift needs to overcome, but the weight will always be pulling down. Why doesn't that couple straighten out? What we need is a balancing force. And this is where a large number of students, and I won't be mean to say some qualified pilots, but some qualified pilots also make this mistake. So we have the weight acting further forward, the lift centre of pressure acting back. In order to keep this balance, we need another acting force to pull down, to be that seesaw. And so this is where the tail plane comes in. See, I told you all you flex wing pilots to switch off. So here's the weight, that's doing this. Here's the lift, that's doing this. It wants to do that. And so we need this tail plane to be generating a downforce to cancel out the weight. And this is why it's positioned so far back to act as a lever arm, like a seesaw. Now, so it doesn't act up. It's a tail plane. It is a plane all by itself. This is the main plane, this is the tail plane. If it was acting lift, obviously it would lift the tail up. We need it to push the tail down. And so when we're talking about aerofoils before, if the main wing is this way, which way should the tail plane be? The camber should be on the underside, because the lift or lifting force, centre of pressure, needs to be on the underside. And so a tail plane should be also at a negative angle of attack in relative to the relative airflow. So a tail plane should be so if I put in a relative airflow, you see we have a positive angle of attack here and a negative angle of attack here. And so we have a downward force with the tail plane. So now the forces are balanced. But this is also where we bring in the definition, here we go, movement about the lateral axis around the longitudinal plane. So we have one force balancing out the other. The tail plane is there. However, what happens if we are moved about this axis, so not necessarily a control, we go over maybe a thermal or a bubble and the nose comes up. Watch the tail when I do the same action. See how the tail plane changes? What's happening here is we have the main plane at a positive angle of attack and the tail plane at a negative angle of attack. Now as the main plane is lifted, can you see how the angle of attack at the tail changes? Yeah? What happens is, as this lifts, the angle of attack changes to a point where it may go into a positive angle of attack. So if this tail plane is now generating a positive angle of attack, this tail plane now produces lift in the upward motion and it brings the nose back down again to the point where it's now bringing down force. So the tail plane is acting as a balancing motion. Now flex wing pilots, how long ago did you switch off, in all honesty? Woody, are you still with us? A flex wing is exactly the same. Here's one I prepared earlier. So a flex wing or a delta wing, which is what we really need to refer to, is you can see the shape. If we say that the weight is here, so say the weight is here, and we'll say that this is the centre of pressure, you can see that everything behind the lift is aft of the centre of gravity. Now I don't know if you've noticed, you flex wing pilots, if you look out when you're flying, here's my flex wing, if you look out to the wingtips when you're flying, what angle are the wingtips at? They're at a angle something like this, aren't they? A negative angle of attack. So therefore, in these portions here, where we have a negative angle of attack, these wingtips are producing a downward force motion, pushing down. This is pushing up and the weight is pushing down. So again, just like the tail plane on a traditional aircraft, a delta wing incorporates the tail plane within its wing and therefore makes the aircraft very, very stable in flight, which is why it's one of the nicest aircraft. Now, flex wing pilots, are you aware of the washout rods? So some special prize if you can tell me what the washout rods do. We'll see if anyone gets the answer right. What do the washout rods do? And I want a proper description. Proper, so from Stoke. Okay, so that is longitudinal stability. How does the aircraft keep the latitudinal axis in its right position? Tailplane. Now, we talked about weight and balance before, or mass and balance as it's been coming on, and this is where we can influence the stability of our aircraft, because an aircraft designer will also build in tolerances for this centre of gravity, where it can be moved further aft or further forward. With a heavier aircraft, there is more weight on the nose pushing the nose down. Therefore, increasing the weight means that we will increase the force of the balancing force of the tailplane. And if we exceed that centre of gravity, we may make the aircraft more difficult. It will be more stable because it's heavier, but it also will be a lot harder to manoeuvre that aircraft in pitch. And vice versa, if we move or we're flying very, very light, and we are reducing the weight, therefore the tailplane won't need to do as much action or lifting, balancing motion, and therefore the aircraft will be more controllable. And so for me, particularly as a flex wing pilot, I've already mentioned I didn't used to like flying in thermals. Now they're good fun, or free fuel as it was point to me. I used to fly heavy. I used to be pretty much on my maximum takeoff weight because it made my aircraft more stable. Didn't exceed it, but you know, I certainly flew with as much fuel as I could carry, which is always a good thing to have more fuel than you actually need. But its main purpose was that it made the aircraft heavier and therefore made the aircraft more stable. So you guys that don't like flying in thermic conditions, load your plane up a little bit more. You know, we're probably only going for a flight anyway, so a slightly heavier plane is going to make that aircraft more stable. Okay.
So some answers from Flexwing pilots here.
Go on.
Right. Ben Ashton says they wash out things like rods. Right.
Close.
Danny Kay says limit movement. To which my reply was, Danny, why and for what reason would they do that? Yeah. Cactus Mart says prevent tip stall. Angus Young says.
Oh, hang on, go back to Cactus Mark. At what speed?
Yeah.
High speed or low speed?
Yeah. Angus Young keeps wingtips up. At what speed? Again.
I still haven't had a right answer yet. You keep going and we'll come back to it.
It's to do with the wing stalling at different AOA. Angles of attack.
The washout rods do one specific purpose job. We'll come back onto it. Okay, so let's talk about stability in roll. And this is not us putting in an input. This is the aircraft gets lifted up by one wing. Why does the aircraft return back to its original state? Now this is an easy one. And again, relevant to 3-axis, relevant to flex wings, relevant to paragliders. Because it's all to do with weight shift. So again, this is as much as a flex wing. We have a wing, and we have the weight. If this wing gets lifted, the weight is also moved. It moves this way. Just like a grandfather clock, that weight wants to come back to the centre. It wants to come back acting down. And so where here lift is opposing weight, this sets up a couple where it is off to one side. That weight wants to return back to its original state. Very, very simple, the weight shift. Same with flex wings, paragliders, anything that's the weight is hanging down. As that weight is moved out, it will want to swing back. There is a slight difference with low wing aircraft. So here is our weight. This is where it incorporates what's called dihedral. My wings kind of level. And these are wings that are a higher at the tips than at the root. Is there any dihedral in this one? No dihedral. And what happens is, as this changes, as this lifts, it changes the angle of attack on one wing. So therefore, one wing, ultimately it starts to slide. It will slide as well. But as that airflow is travelling over the wing and the different angle of attack on one wing, it will return it back to its original state. So that the lift or the forces of the wings return back to its original state. Now some fixed wings, so like a Sky Ranger, still a high-winged aircraft, but you will also see as an element of dihedral in it as well, making the aircraft a very nice aircraft to fly, one of my favourite aircrafts to fly. So dihedral, with a slightly, here we go, there's a better picture. So the wingtips raised higher than the root. The lower wing makes airflow at a higher angle of attack. The lower wing generates greater lift and restores the aircraft back to level flight. Simple. Yet we're flying along, and the first thing that happens when the aircraft does this is we can't wait to put an input in. We're now increasing that stability, and the aircraft will go over the other side, and now we're fighting the aircraft. This is what sets up that yawing, or that yo-yoing on the way into final. We're all set, everything's looking great, we get some movement because we're closer to the ground, so the bubbles are probably happening, and we put an input, and now we're in this oscillation where we are fighting the aircraft instead of what you see your instructor do, wait for it to come back.
We get a lot of that on the students on the winch when they're new, when they're going left hand control, right hand control, left hand control.
Yeah, yeah.
Just all the way along.
Same with flex wings, and you see it a lot. People just start counteracting the aircraft. You know, leave it alone. The least complex thing, or the most dangerous thing in most aircraft or flying machine, is the pilot. The person who designed the aircraft tends to know a bit more about it than we do. And so some examples here we can see is a Piper Warrior. So this is a low wing configuration. Pendulum effect's very weak, but you can see the dihedral there is quite pronounced. Next one down we have the standard Cessna, or a high wing configuration. Pendulum effect is very strong, but less dihedral angle. There is actually some dihedral in them. Now here is one, the Antonov AN225, massive plane, largest cargo plane. And if you look at the tailplane there on how far apart they are, but look, the wings are angled down, so it's a high wing configuration, but the wings are angled down. It's called anhedral. And what they've done there is they've built in, because this aircraft is so difficult to maneuver, you can see the control surfaces on this plane. The aircraft is so difficult to control that they've had to build in instability in order to control the aircraft. Again, aircraft designers knowing what they're doing more than we do. Now, when we're talking about stability in the vertical plane, i.e. yaw, it's very, very simple. Aircraft are designed like a boat. If you look at this aircraft, it's very, very streamlined. Now if I put a slight angle on this, you can see that it's very broadside. And so if this is the direction of travel and all of a sudden we get a movement, the relative airflow is going to strike every flat surface and weathercock the aircraft back to its original position. Yeah? We're flying along, there's the gust, weathercocks back in. And we've also talked about this, because this is the one mistake that people also make. Same with a flex wing. So there we go. Slight deflection, all these flat surfaces aft of the centre of gravity. So centre of gravity is forward, all the flat surfaces are behind it. It pushes the aircraft to the rear. With a dihedral wing, this wing accelerating changes the relative airflow and brings the aircraft back into level. So more lift, more drag, aircraft comes back. But on a tailplane, here we go. Let's put in a tailplane. As the relative airflow is travelling this way, it's moving around the rudder. If we change the relative airflow, this wing is now acting like an aerofoil. So Here's the angle of attack. That's a positive, so the aircraft will move, generating lift in this direction, and move back into the relative airflow. And so the tailplane, or the rudder, acts just like a wing. In fact, if I was to put the wing this way, it looks just like a standard wing. And it does exactly the same. It generates lift in either direction that we're asking it to go. So not just a weathercock, it's an actual wing that uses the same principles as the main plane and the same principles as the tailplane. Okay, so that's about it on stability versus control when we're talking in the basic sense. Normally now I would go into details with you on your specific aircraft. So if we were a flex wing pilot, we'd look at flex wing. If we were a fixed wing pilot, we'll look at the control for flying a fixed wing. So what I want to try and do is bring in two primary effects of controls and then further effects of controls. Because a lot of people, most people, are aware of the primary effects of controls. And so this is where I would normally, again, if you were a fixed wing or a flex wing pilot, be in mind of which one is. So we will put the control, the input that will be there. We have the primary effect, the further effect, and more importantly, the use. So when we try and make it an R. So when we're looking at control, what we'll look at is the actual axis. And so let's look at pitch. Now we can pitch the aircraft up and we can pitch the aircraft down. Now the primary effect of pitch up is that the aircraft starts to climb. We generate a higher angle of attack on the wing, it generates more lift. The aircraft starts to climb, and vice versa, pitch down, we reduce the lift, the aircraft starts to descend. Okay, so that's pitch. When we're looking at roll, we can go left and we can go right. Primary effect is very, very simple. We roll left. My OCD on the colour needs to kick in. We roll left and we roll right. And then when we're talking about yaw, we can yaw left and yaw right. And again, yaw left and right. Shall we do power? Okay, we can also do power as well, just for those of it. And when we're talking about power, we can increase and we can decrease power. As we increase power, think of yourself on the runway, we're on the runway, we're stationary, we increase the power, the aircraft starts to accelerate. And if we decrease the power, the aircraft starts to decelerate. This is what most people are aware of when it comes to aviation. We pull back on the stick, the nose goes up. We roll it to the left, we roll left. The further effects are what we need to be aware of as pilots. Because, based on the aerodynamics and the build of the aircraft, if I pitch up, the air travelling over the wing is now generating more lift. But lift generates induced drag, which slows the aircraft down. And so the further effect of pitching up as the speed decreases. And therefore pushing the nose down, yes, we start to descend, but that reduction in lift is a reduction in drag, and therefore the speed increases. Now again, fixed wing, flex wing, I appreciate there's a difference. What we have when we come to roll is that the aircraft will roll. Again, thinking of what's happening here is that we're using ailerons in order to make this happen. And you see that the ailerons change the chord line of the wing. So this wing is generating more lift. This wing with a negative angle of attack reduces lift. So based on the theory that more lift produces drag, the upgoing wing generating more lift slows down. And the downgoing wing generating less lift accelerates. And this is what's called adverse yaw. The aircraft not only rolls, but it also, I'll do it this way, not only rolls, but it also yaws in the opposite direction. It's called adverse yaw. So an aircraft would do this in flight. Adverse yaw. So the further effect of roll is yaw. We also have a situation where, as we're increasing the angle of attack, the aircraft starts to slip and becomes nose down. So at higher bank angles, we'll start to descend as we're losing lift. When we're in yaw, the same principle happens. The aircraft will yaw. We know this happens. If I do this example again, we can see that this wing is travelling faster and this wing is travelling slower. In that theory, when we yaw, this faster wing, airflow over the wing, generates lift. So the secondary effect of yaw is roll. And that's pretty much why we have control of the rudder on a 3-axis, or most of the axis. So the further effect of yaw is roll. And so, sorry, do the final one. Power. As we increase power, we start to accelerate. As we start to accelerate, there's more airflow going over the wing, and therefore the aircraft will start to climb. Reduction in power, or reducing the power, the aircraft starts to decelerate, we lose lift, the aircraft starts to descend. And so you can see that as pilots, if we want to climb, we also know that we're going to lose airspeed. And so we need to increase the power in order to climb. And this is where we're setting up the power and pitch couple. Fixed wing pilots, if we are rolling left, we know that the aircraft is going to yaw. So therefore we need to yaw left in order to roll the aircraft. And this is setting up that stick and rudder couple. So we work power and pitch together. If I wanted to slow the aircraft down, let's work this in reverse. If I start to decelerate, I know I'm going to descend. I don't want to descend, so therefore I would pitch up, so the aircraft would climb. Again, using the same principles, power and pitch, one to climb and the other one to slow down, so power and pitch couple. Why will we use these? Predominantly we use pitch for speed. Why would we use roll? Very, very simple. It's for turning. Why do we use yaw? Balance. And why do we use power? Height control. This one is the one that most people get wrong. We ask people to, or we say, what's your airspeed? And the first thing they do, or only thing they do, is increase power. Now, if you increase power, yes, we'll temporarily accelerate, but that extra airflow over the wing turns into lift. So you've got to cancel that out with pitch. So remember, pitch, speed, roll for turning, yaw for balance, and power control for height. Okay, that's it for me. Did we get any right answers on washout rods?
Tell them why.
Okay, so what can we use as a washout rod? So flex wing pilots, if you look at your wingtips are at a negative angle of attack, and your washout rods are sticking out like this. Yet when we're on the ground, the wingtips are resting on the washout rods. When we take off, we know that this force, the airflow, is pushing this up. When we're at a slower airspeed, we need to push the bar forwards. If we're pushing the bar forwards, the angle of attack at the wingtips decreases even further, so it's a higher angle of attack. And so if the aircraft stalls, yes, it will then fall onto the washout rods, but the wingtips should remain flying, hence the reason why they are there. The washout rods are when we are pulling back on the bar, therefore reducing the angle of attack of the flex wing, and therefore the washout rods are there. So the washout rods are there to prevent a high speed stall. If we pull back too far and these wingtips went past their usable angle of attack, we would lose the downward force at the wingtips, and therefore the aircraft would do this. There are examples. So the washout rods are to maintain the angle of attack at a high airspeed. Okay, are we all good? Any questions? What time? 1 minute to spare. It's like we've done this before. Do you want to come on and say goodbye?
Can do if you want.
Right. Thanks ever so much. As always, please do feel free to send in all of your questions. We do enjoy chatting to you guys. Again, Facebook police, please feel free to pull us up on something that you think we may not have explained properly. It's certainly our job to explain it properly. And thanks again. We're over 250,000 hits at the minute, which is amazing. And I'll see you next time.
Stay down, similar to luff lines, keep the trailing edge high all the way to the wings.
Nothing to do with luff lines.
No, no, nothing to do with luff lines, David. Luff lines alter in flight with speed. They alter the reflex in the wing. That's what reflex is. So it alters the reflex. It's pitch stability within a delta wing isn't just the wingtips as well. It's sweep back, we've got washout, we've got reflex within the wing. So we've got a complete, a good flex wing or a good delta wing, hang glider, call it what you may, is the most stablest flying surface you can get. Yeah, especially in pitch.
That's why they're on fighter planes.
Yeah, that's why they're on fighter planes, exactly. Very manoeuvrable and very very stable. So we'll be back on Thursday. Enjoy the weather. Like I say, you know, get out there, grow your tomatoes, build your brick walls. That's what we're doing. We'll be back on Thursday, 7 o'clock. Any questions? Please put any questions to us that you wish, and we will answer them on the next one. And we'll also do a little weather report as well on the next one. See how the weather's going to change. And until then, yeah, stay safe. Stay well and stay at home. Alright, till then, see you next time, guys and girls.